Our fourth colligative property is osmosis and osmotic pressure. So osmotic pressure is the actual colligative property, but osmosis is necessary for us to discuss before we can understand this. If you have already studied it in biology, then you probably talked about it in more detail, and if you haven't yet, then you probably will if you're a biology major. So let's talk about what osmosis is first. So most of these scenarios for osmosis are a little bit unfamiliar, so after a little bit I'm actually going to talk about a familiar example of this as well. So the idea with osmosis is that you have a system that has a semi-permeable membrane. Maybe I'll make that a different color. A semi-permeable membrane like a cell membrane in between here. You can also imagine some kind of a durable filter material that allows some things to cross it and then other things not. So here's our semi-permeable membrane. And then the black parts are just intended to be the sides of a container. So on one side of the semi-permeable membrane, we have maybe it's a pure solvent, like water. And then on the other side of this material, of this semi-permeable membrane, let me label it. This would be some kind of a solution. So a physical analogy that you might think of would be, this would be a very strange scenario to set up, but let's say that you had a soup pot or something like that, and you took a sieve or a piece of cheesecloth or something and you put it in the middle. I guess we'll make it green for our semi-permeable membrane as well. So here's our cheesecloth. And cheesecloth, of course, is porous. And so if you have soup on one side of it and you have water on the other side of it, then the water can mix between both of these two, but the big chunky pieces of the soup are not going to be able to go through. So that would make this a semi-permeable membrane. Now, the analogy breaks down pretty quickly because other things will happen with the, other things are permeable in both directions that are not permeable in the case of our semi-permeable membrane here. So cell membranes are the main ones that we are looking at here. But you can also have some artificial membranes that are similar to this. Okay, so what happens if you have a pure solvent, like maybe water on one side and maybe seawater on the other side? What's going to happen to this is that the pure solvent is going to flow across our semi-permeable membrane and it's going to dilute the solution. So that means that what would happen after a while is that you'd end up with, here's our permeable membrane, semi-permeable membrane. Here's your water, and then you're going to have that water level drop down a bit, and your seawater level is going to increase a bit because the pressure of this pure solvent is going to, or excuse me, it's really the other way around. The pressure of the seawater is going to end up pulling the pure solvent into it to dilute it. And so you're going to end up at some point with this differential height that relates to the pressure difference initially between these two systems. So let's think about the pressure of all of these things. We have atmospheric pressure, and that's just the pressure of our gases, right? And if these are open containers, then atmospheric pressure is pushing on both of them. But then we also apparently have this thing called osmotic pressure. And osmotic pressure is, it gets the Greek letter pi This is a capital pi, so lowercase pi is what we use in math, and we would use this symbol for lowercase pi. This is a capital pi, and the reason why we're using it is because pi is the Greek letter that's equivalent to the Roman p, and we always use p for pressure. And just in case you weren't familiar, the letters that we use for our alphabet, these are Roman letters. These are Greek letters. So we have different alphabets that we use for different things. And since Roman letters are used for our regular writing, all of these are Roman letters, the Greek letters tend to be used in science and math for special stuff. Okay, so you can calculate the osmotic pressure. This will be equal to the molarity of the solution multiplied by the gas constant and the temperature. So these three are all the same. And of course, if we want to include the Van Hoff equation, or excuse me, the Van Hoff factor, which we should, we're going to include that explicitly here. All right, so just to be really clear, this is molarity, so moles per liter. This is our gas constant, the same one that we used for ideal gases. And this is our temperature in Kelvin. And of course, the Van Hoff factor. All right, so if we look at the units, the Van Hoff factor is unitless, so we have moles per liter. We have the gas constant, which will be liter atmosphere per mole Kelvin or liter bar per mole Kelvin. So I'm going to put bar as an alternative. And then the temperature is in Kelvin. So if we look at how that's all going to cancel, the kelvins cancel, the moles cancel, the liters cancel. So that means that our osmotic pressure is going to have units of either atmospheres or bar, depending on which gas constant we use. So it really is a pressure unit. And it's really a pressure unit that is a little hard to get your head around why it's a pressure. And I don't think we're going to worry about spending too much time about why there's pressure on this, and we'll just accept it and say, okay, there's pressure because this concentration, this solution has stuff that's dissolved in it. So you can see that the only things that are going to have osmotic pressure are going to be solutions, because they're the only ones that have stuff dissolved in the liters of their solution. So pure water exerts no osmotic pressure. By itself. But since every other solution is going to exert some osmotic pressure, then water, in contrast to that solution, is still going to end up being involved in the osmosis. Okay? So let's do a quick calculation, and then let's talk more about some of these principles here. All right, so in this scenario where we have water on one side and we have seawater on the other side, let's calculate the osmotic pressure from the seawater. So seawater has a lot of different things dissolved in it, and we can find that its concentration, its molarity, is approximately 1.15 molar of all kinds of dissolved stuff. Let's go ahead and have the temperature be 25 degrees Celsius. And we need to know the Van Hoff factor. It turns out that the Van Hoff factor is a little bit under 1, and we're not going to worry about why that is either, but this is still going to be useful information. Okay, so do we need anything else? We just need to pick which gas constant we're going to use. So let's go ahead and stick with the atmosphere gas constant. So we're going to calculate the pressure of the seawater. So our equation says that we need the Van Hoff factor, 0.92. Remember, that's unitless. And then we have the molarity, 1.15. the gas constant, 0.08206 liters atmosphere per mole Kelvin, and 298 Kelvin is our temperature. So our pressure, once we do all this calculation, is going to end up being 25.9 atmospheres. That's pretty high. That's a pretty large pressure. So what do we do with these kinds of pressures? Well, it's a little hard for us to figure that out yet, so it might be easier if we look at another example where this is one that we're going to visualize, that we're actually going to see in the book. So I'm going to draw what they have here. They have this little tube, and on one side they have 0.1 molar NaCl. I guess this would actually be 26 atmospheres since we're only keeping 2 sig figs. Sorry, I just noticed that. And then 1.15 molar seawater. So what would happen when we have not pure water on this side, but seawater on one side and a constant or a dilute sodium chloride solution on the other one? We've already figured out that our pressure from our seawater is 26 atmospheres. So let's see what the sodium chloride is going to be pressing on. So sodium chloride is going to have a Van 't Hoff factor of 2, and it has a concentration of 0.1 molar. We'll use the same gas constant. And then 298 Kelvin. So our pressure is going to end up being 4.9 atmospheres, right? So we have two different pressures. On the sodium chloride side, we have 4.9 atmospheres, and on the seawater side, we have 26 atmospheres. And what that's going to do then, since the seawater is pushing harder, it's going to draw the water from the sodium chloride solution over into the seawater. And so the pure solvent inside, I guess we can't say it's a pure solvent, but the solvent from inside the sodium chloride will be drawn into the seawater to dilute it, which will reduce its pressure. So let's switch over and take a look at the book and see how this would look. This is figure 1123 from our book. And so on the left-hand side, I guess they have their seawater and sodium chloride reversed. Anyway, it's fine. So on the left-hand side of this diagram, we have the seawater, and on the right-hand side, we have the sodium chloride. And the solvent molecules, so you can see them in here, the solvent molecules are going to have a net flow over to the left to dilute the seawater. So you can see after some time, then more water, more total solution is going to have gone onto the left-hand side, and eventually our flow will be even across, so water will continue flowing, but we won't have a net flow in one direction. So that initial difference of osmotic pressure is going to lead to a total height difference between these two that's going to relate to this overall gravitational pressure difference. We are not going to worry about how high this would have been. It's something that you can connect with in physics class if you really want to, but it's not really necessary for our conversation about osmosis in this chapter. Suffice it to say that what we have going on in this whole scenario is we've got atmospheric pressure pushing down on both of these. You have this extra pressure of the seawater pushing against the membrane and not allowing its water to flow out of it. And that's going to allow the water on the other side to flow in. And enough is going to flow in until the atmospheric pressure pushing down here on the water is equal to that height difference in gravitational pressure here. And then you'll get your overall osmotic pressure difference based on osmosis. Okay? Now, I hope that this diagram hasn't confused you in this conversation about differences in osmotic pressure. What I'm really trying to get at is this qualitative sense that on the more concentrated side, that's the direction that the water is going to flow into. That the net effect of osmosis is to try to dilute whatever your solution is to make it less concentrated. So let's go back and take a look at a general diagram here. So our general diagram is that if we have this container with a semi-permeable membrane in it, and we have some, I guess we better make them concentrations. Some concentration on one side and another concentration on the other side. If M1 is greater than M2, so if the concentration on the left-hand side is more concentrated, then that flow is going to be of the solvent is going to flow into M1, and later you're going to end up, I guess it's not just that the concentration is less. Let me be a little bit more clear. Probably the concentration is less, but overall we have a scenario where our pressure of 1 is greater than our pressure at 2. And of course this is I times M times R and T, I times M times R and T. So presumably these both have the same temperature and they both have the same gas constant. And so what we're really saying is that whatever this combined I1 M1 would be greater than the I2 M2, okay? Because that would be what is the pressure that's happening here. So here is my new concentration because it will have been diluted. So M1 prime is less than M1, and M2 prime, because it's lost some of its water, so it's become more concentrated. M2 prime is greater than its initial concentration. And so ultimately, at the end, our pressures will be the same. And they become balanced. And that happens because the combination of our new I times M1 prime is equal to our I2 times M2 prime. Okay, so those are the parts that are going to come into play here. Okay, so we've had a general sense for what osmosis is. So let's go ahead and redefine this. Osmosis involves a solvent, usually water, but doesn't have to be, moving across a semi-permeable membrane toward the more concentrated solution. So that it will dilute it. And the osmotic pressure is that pressure of the solvent against the semi-permeable membrane, preventing its solvent from moving across the membrane. So you may feel like these are unfamiliar and new concepts, but you have experienced them most likely. So one of the ways that we encounter this a lot is with eye drops. So one of the things that people do when they make eye drops is they make sure that they are isotonic. Let me rewrite that in. Got a little funky there. Isotonic means that it has the same concentration of stuff. And specifically, stuff in your body. So when you put eye drops on your eye is effectively a semi-permeable membrane. And you don't want to put osmotic pressure on your eye and make your eye potentially try to swell or something like that by putting pure water on the outside of your eye, or by putting some really salty or something like that water on your eye too, because that would also put pressure on your eye. It would want to ooze water out. Ew, that's gross to think about. So instead, you make sure that you put an isotonic solution on your eye. It's got the same concentration as the stuff inside your cell membranes, and so it doesn't cause any osmotic pressure, which then makes sure that it's gentle on your membranes. So if you've ever made a saline solution, which is about 1/4 teaspoon of salt, table salt, NaCl, in 1 cup of water. And anyway, this is effectively isotonic with your body as well. So it's better to use a saline solution if you need to clean out a cut or something like that, because it's going to be gentler on those poor exposed cell membranes because it's isotonic. So this does have some practical applications, this knowledge. The other practical application that knowledge about osmosis tells us is that if you think about what's happening here, let's think about that semi-permeable membrane again. Here's our semi-permeable membrane. And let's say that we have some pure water over on this side. And then we have some seawater on this side. And we said that we know that our natural direction is for the water to flow into the seawater. And the pressure from that seawater was like 26 atmospheres or something really high. So this really is a pressure. So imagine a scenario here where we now cap this off and we squeeze it. And let's say we put a pressure on this on top that is more than 26 atmospheres. Let's say that it's maybe 30 atmospheres or something like that. This pressure is now greater than our osmotic pressure, and so it's going to force some of the water, some of the pure water, to go from the seawater across that semi-permeable membrane because we're pushing on it harder than its osmotic pressure is pushing in the other direction. So this is a process called reverse osmosis. And it's reverse because we're making the water go in the opposite direction that osmotic pressure would normally have it go. Reverse osmosis can be used to purify water. And it does a really good job of purifying water. You can get basically everything out of that water, and you can turn brackish, which is slightly salty, or very salty seawater into pure drinking water. The only problems are that because you have to have a pretty strong membrane here and they get clogged pretty fast, are that it tends to be expensive. And so even though drinking water and sources of clean drinking water are a really serious problem around the world, reverse osmosis can be a useful solution in some places, but only places where the communities are pretty wealthy, because changing out new filters and also even pressurizing the system is going to be challenging in terms of mechanics in getting this to work. So there are other cheaper strategies for purifying water, but reverse osmosis is worth mentioning just to kind of know about it. Now I'm going to do one more video on these colligative properties that give us a little realistic look at what is happening under a real circumstance with a semi-permeable membrane. And so in that one, I'm actually going to invite you to do the experiment yourself as well. Maybe I'll just go ahead and give you that little prep information. So what we're going to do in our actual experiment, and you can try this at home, it's a lot of fun. So I want you to take a raw egg. Here's your ingredients list. And then you need some vinegar. Just white vinegar is fine. You need a jar or some kind of a container. And that's basically it. So you're going to take your jar, put your egg in, and put your vinegar on top of it. This is for the first part of the experiment. Anyway, for later, for the second part, you might need tap water, and then either a salt solution or a sugar solution. And I'll talk more about what that is a little bit later. But it would be a great review for you to think about, well, first make observations of what happens when you put the egg in the vinegar, and leave the egg in the vinegar at least overnight, okay? Probably you're going to need about 2 days. So make your observations and then maybe think about writing a balanced equation. So you can think about the chemistry of this kind of an activity as well. All right, so go ahead and get that set up and have fun, and then we'll look at what happens in the next video.